Everyone, today we are going to talk about just-in-time compilation or JIT in Java and Python. JIT is a powerful technique that helps improve the performance of programming languages that are traditionally interpreted. We'll explore how JIT works, its role in the Java virtual machine and Python, and why it makes programs run faster. Let's get started. What is JIT compilation? Before we dive deeper, let's first understand what JIT compilation is. Just in time compilation is a technique used in modern programming languages where the code is compiled during execution rather than before execution. It bridges the gap between interpreted and ahead of time compiled languages, optimizing performance dynamically. Why is JIT needed? Traditional interpretation is easy to implement but slow because it translates code line by line during execution. Whereas AOT compilation, on the other hand, compiles everything beforehand, which speeds things up but makes programs less flexible. JIT provides the best of both worlds. It starts by interpreting the code and then compiles frequently used parts, known as hot code, into optimized machine code while the program is running.
Starting with how JIT works in Java. Number 1. What happens at compile time and runtime? Let's walk through what happens when a Java program runs. At compile time, our source code is converted into an intermediate form called bytecode by the Java compiler. This bytecode isn't platform specific. It's designed to run on a system that has a JVM, making Java platform independent. Now at runtime, the JVM first starts interpreting the bytecode line by line, but interpretation is relatively slow compared to native execution. That's where the just-in-time JIT compiler comes in. It monitors the execution, identifies the part of the code that are run frequently. These parts are called as the hotspot or hot code. Once such hot code is identified, the JIT compiler translates into native machine code which can be executed directly by the CPU. And here's the smart part: the compiled machine code is cached, meaning it's stored so that the same code doesn't need to be recompiled every time it runs. This significantly boosts performance over time, especially in long running applications. JIT in Python. Python is known for being simple and easy to read, but not always the fastest when it comes to execution. By default, Python uses something called CPython, which is an interpreter. That means it reads the code line by line, which is slower compared to compiled code. That's where JIT compilation comes in to speed things up. One of the most well known JIT implementations for Python is PyPy. Instead of interpreting every line every time, PyPy uses a tracing JIT. Here's how it works in simple terms. PyPy watches which part of your code are running again and again, like loops or frequently called functions. These are your hot code paths. Then it records this path and compiles them into machine code. So the next time they run, they execute much faster.
Next up, we have how JIT optimizes code execution. JIT compilation applies several runtime optimizations to improve performance based on actual execution patterns. These optimizations are adaptive and context aware. Let's go over a few key ones. First, we have inline caching. Imagine you are calling the same method many times. JIT remembers where that method lives so it does not waste time searching for it again and again. Then there is loop unrolling. Normally, loops check a condition every time they run. JIT expands the loop into repeated code blocks so it does not need to check that condition every time, which saves time. Then we have dead code elimination, which removes code that's never going to run, like an if statement with the condition that is always false. This makes the final code smaller and faster. With constant folding and propagation, if you have got calculations using constants like 2 plus 3, GIT solves it while compiling and replaces it with 5, so it does not waste time doing that later. Escape analysis is a memory optimization. If a temporary object is only used inside one method, GIT puts it on the stack instead of the heap. Stack memory is faster and does not need garbage collection. And finally, functional inlining replaces short function calls with the actual code of the function. This removes the need to jump to another place in memory and helps speed things up. These optimizations are applied based on how the program runs, which is why JIT can generate faster machine code than traditional compilation. So, when is JIT actually helpful? Let's look at a few real world examples. Imagine a Java game engine. The program runs for a long time and it keeps calling the same functions like render, update physics, etc. JIT identifies these hot methods and compiles them into optimized machine code, improving performance as the game runs. On the flip side, think of a small script written in Python that just renames a batch of files or sends a quick mail. It finishes in a few seconds. GIT does not get the time to analyze and optimize anything, so there is no benefit. Also, if your program is doing heavy input output, like reading large files or waiting for network responses, CPU optimization is not the bottleneck, so JIT won't help much. And if you are on low power devices like microcontrollers or old phones, GIT's extra memory and CPU usage could even hurt the performance. So, in summary, GIT shines in long running CPU heavy programs, but for quick scripts or IO based apps, it may not be worth the overhead.
Trade offs of GIT compilation. GIT compilation brings a lot of performance advantages. Once the program runs for a bit, the GIT compiler identifies frequently used parts or hotspots and compiles them into optimized machine code. This makes the program run faster over time. It also adapts to real runtime behavior, applying dynamic optimizations based on what's actually happening, like frequent loops or method calls. But there are trade offs. GIT introduces a warm up delay at the beginning since it has interpreting code. It also consumes more memory as it stores compiled versions of the methods. Implementing a GIT system is complex and adds overhead to the language runtime. And in the case of short lived scripts or programs that mostly perform input output operations, GIT may not have enough time to show any real performance gain. Conclusion. Let's wrap up with a quick summary. We saw how JIT works by compiling frequently used code at runtime for better performance. We compared how Java and Python use GIT, Java through the JVM and hotspot, and Python via tools like PyPy or Numba. GIT gives us faster execution, real-time optimizations, and adapts well to long-running programs. Looking ahead, JIT is evolving with adaptive compilation techniques and even machine learning-based optimizations, which make more performance tuning smarter and more automatic. In short, JIT blends the flexibility of interpretation with the speed of compilation, making it a powerful technique in modern language runtimes.